our next speaker, Mikko Salminen, who is with Jensen Hughes, and Mikko is structural fire engineering lead for Europe for Jensen Hughes. Mikko, the floor is yours.
Thank you, Thomas. So the topic of my presentation is thermal and structural analysis of timber columns in traveling fire, and I will present a case study, a lot of more studying before that, but finally a case study. So the contents shown here. So first some introduction, background and motivation for this whole study, and then some validation and comparison to test results, and I added some parametric studies also because this is quite interesting topic, and finally the case study, which includes some traveling fire analysis and of course SAFIR analysis with thermal and structural side also, and finally a summary. So starting from the introduction, a really short one here. So I think I've been SAFIR user like almost 10 years now. So I pretty much started with steel structures. I only did steel structures like a few years basically, and then I have moved to more to details and composite structures also. But last years the timber projects have increased in number really considerably, and I have to admit that in the first timber analysis I just usually analyze the char depth, and now as this presentation will show, and we have a lot of data from many research that the charring analysis typically is not enough, especially if we are in other fires than standard fire. It's really important to analyze also the structural behavior. But anyway, it's great to present here. I mean, a couple of figures there. Pretty much first presentation I did about my SAFIR case was Helsinki Olympic Stadium, and this hybrid structure here is one of the last ones. So it's always good to get some feedback of these studies. And yeah, moving to background and motivation. So I guess you all know that timber is totally and fundamentally different building material than non-combustible building materials like steel and concrete, as it is of course part of the fire load also. So that makes it really complicated in many ways. And just a couple of notes from the regulations from Finland. In performance-based design, basically you need to make sure that the building elements are able to resist the full fire, including the cooling phase in higher consequence building. And in Britain they use SDA guidance, and it says pretty much that higher consequence buildings should have adequate likelihood of surviving burnout, and self-extinction must be demonstrated with the structure capable of supporting the applied load during and beyond the fire. So even showing that the structure survives the cooling phase may be challenging, not even going to self-extinction, which is totally really challenging topic. And fire tests show that the failure may occur late in the cooling phase. So that means that calculating or analyzing just the char depth is often not enough. So now moving to validation and comparison to test results. So for this purpose, we were interested in fire tests for natural fires and with cooling phase. So Cherney and others have nice tests for timber columns, and they have conducted the tests in SAFIR and in fires that had 10 minutes and 15 minutes duration of heating phase, so DHP. And these are shown in the figure on the left-hand side, these curves. So they are referred here as DHP 15 and DHP 10 and SAFIR. So in these fire tests, the column resisted the full DHP 10 fire, but it failed at 98 and 153 minutes of DHP 15 fire. so really late in the cooling phase. And we were, of course, interested if SAFIR could capture this behavior in the analysis also. So this slide presents the 2D thermal model of the column cross-section and the 3D structural model constructed from beam elements. So pretty simple models, and everything was modeled as close to the tested configuration as possible. And here are some results. The figure on the left shows the maximum char depth at approximately 20 minutes in the case DHP10. And on the right-hand side, we have the char depths as a function of time in different cases. So in SAFIR, the charring is pretty close to the Eurocode value 0.65 millimeters per minute. And in the case DHP10 and DHP15, the maximum char depth is reached very early, around 20 to 25 minutes. And the maximum char depth is around 12 or between 12 and 16 millimeters, so not too much. And this one shows the horizontal displacement on the left. So it can be seen that in SAFIR, the displacements grow quite fast after, say, 30 minutes or so. And in case DHP15, the failure seems quite sudden. And in case DHP10, the displacements seems to stabilize after, say, a couple of hours. And the summary of the failure times is shown on the right-hand side. And in SAFIR, SAFIR was quite a lot on the safe side, 47 minutes. For the failure time, as in test, it was 55 and 58. And in the case DHP10, the result was the same as in the test, so there was no failure. And in the case DHP15, SAFIR predicted the failure time really well in the cooling phase and was a little bit on the safe side. So overall, I'm really happy with these results, and they give some confidence to use the same methodology in the actual projects. And I guess Thomas has also done similar analysis, so will be interesting to hear if the results were the same, but let's see. So before moving to the case study, some parametric studies. So after modeling the tested configurations, I think I woke a little researcher inside me who wanted to study this a little bit more. Unfortunately, didn't have too much time for this, but I will share some of the interesting findings here. So now it's clear that the failure may occur late in the cooling phase with the timber columns, and even though the char depth doesn't increase anymore. So wanted to study this a little bit further. And if taking closer look at the material model of Eurocode, you can see that the material properties decrease actually quite a lot at lower temperatures than the char temperature, which is around 300 degrees. So in this case, I chose 75 degrees of Celsius to be considered also, because it corresponds close to, say, 50% or 70% of the normal temperature properties, and 50 to 70% may be quite typical maximum loading in fire compared to normal temperatures. So these are the cases that were analyzed in addition to the tested ones, so DHP 11, 12, DHP 20, and DHP 30. So the summary of the failure times calculated with SAFIR is shown here. So in DHP 10 and 11 there is no failure, but in DHP 12 there is a failure really late in the cooling phase, so 161 minutes. And the horizontal displacements are shown on the right hand side. So the failure seems quite sudden in many cases. For example, DHP 12, the displacement seemed to stabilize, but there's a sudden failure at late stages at the cooling phase. And then this slide presents the failure times as a function of the applied DHP curve. So you can see, for example, that there is no failure if DHP is 11 or less, which we already knew. But anyway, and the failure occurs at soonest at 47 minutes if we stay at the DHP/ISO curve. So all the failure points are somewhere above these values, and you could actually draw a nice curve for those failures. Not sure if this kind of curve helps in actual design, but I think this figure may help to understand the failure behavior of timber structures in natural fire. So the test results are also shown here, which are the red balls, and SAFIR is the blue ones. And this one shows the temperature distribution of the columns cross sections in 3 different cases and at 2 different times. So the cases are ISOFIRE, DHP 15 and DHP 20. And the temperature distributions are shown at the moment when the maximum char depth is reached and at the time of the failure. So you can see that in ISOFIRE, the moment of the maximum char and failure is of course the same. But in DHP 15 and DHP 20, you can see that after the maximum char depth is reached, the depth of the 75-degree isotherm still keeps growing, which means that the resistance and stiffness of the column decreases. And studying a little bit more char depth and 75-degree isotherm, they are presented as a function of time here. So the failures are presented with the X mark, and you can see the same here as in the previous slides. So in DHP curves, even if the char doesn't increase, 75-degree isotherm goes deeper into the cross section. And the smaller the DHP, the larger is the difference between the char depth and the 75-degree isotherm. So this clearly indicates that using the same zero strength layers as in ISOFIRE is really dangerous and leads to unsafe results. Okay, finally moving to case study. So this is still confidential office project in Finland, and actually this is a large area where there will be many timber buildings, including offices, which are at least 8 stories high. And in order to justify quite high timber office buildings with exposed timber surfaces, performance-based analyses are needed. So this one is still in the preliminary design at this phase, but the goal is to use exposed timber columns and beams and as much CLT slab as possible. So the figure below shows one potential configuration where there is approximately 30% of exposed CLT in the ceiling. So the yellow color indicates non-combustible protection. So we gave a preliminary requirement for the design team that structure should be at least air 180, so 3-hour protection or resistance in fire. So the Finnish building regulations require in performance-based design the full fire resistance. So here I will present the preliminary results for the case where 30% of the ceiling is exposed, and Sprinkler is ignored in the analysis. Finnish fire regulations would technically allow to take them into account, but conservatively it is not taken here into account in any way. And pyrolysis model is applied in FDS in order to take the fire spread and traveling fire realistically into account. And this model is validated against code-red and other nice studies. I'm not going into details in that in this presentation. So the area of the office floor is about 700 square meters. So it's clear that parametric fire curve couldn't work very well here, also because of the exposed timber surfaces. And there's a short clip of the FDS analysis. Let's see if it works. It seems to work. So you can see that the windows break between 3 and 8 minutes, and at around 10 minutes, the burning occurs mostly close to the windows, and at around 43 minutes or so, the office fire load has mostly burned, and the heat release is mostly from the structures. In this case, the fire spread is really fast, and that's mostly because there is exposed CLT in the ceiling. We also studied the case where there is no exposed CLT and it's more like traveling fire, but in this case, the fire has really spread all around in, say, 10 minutes or so. Okay, moving on, and moving to SAFIR analysis. So the middle column is analyzed here. In the final design, we of course need to check all the other ones and the beams and slabs also. Few different cases were considered here, so we wanted to check also SAFIR, how it behaves there, and also with different loadings. The actual design fire load is the 3,362 kilonewtons, and the 6,000 kilonewtons is the ambient temperature design load. And in all cases, the analyses were conducted up to 4 hours. And the design fire temperatures for the column are presented on the right-hand side. So temperatures get pretty high at around 50 minutes, around 1200 degrees, and the cooling phase is really long. So the thermal and structural models are similar as in the validation study. Of course, cross-section geometry and loading are based on the actual case. And this one shows the charring of the column as a function of time. So it can be seen that the charring rate is clearly higher between 30 to 60 minutes than in standard fire, which is natural because the design fire is really severe. And also some snapshots about the chart portion and the portion that is below 75 degrees. Moving to structural analysis, so there's no failure in SAFIR with fire design load, but there's a failure at 147 minutes if applying the design load at normal temperature, but this was more or less just additional check. And the most important case, the actual design case, is FDS with 3,362 kilonewton load, and there is no failure in that. And also check this one with full normal temperature loading as a sensitive study, and again, no failure. And from the horizontal displacements, you can also observe that in our design case, we are probably not close to the failure, as the displacements have pretty much stabilized in 4 hours. And similar figure as shown previously for the char depth and 75 degree isotherm as a function of time. So you can see that in this case also the 75 degree isotherm stabilizes around 3 hours, which indicates that there will be no failure also at the later stages. Also the char depth and 75 degree isotherm depth in the design case are much smaller than in the case where the failure occurred in SAFIR. So this gives some confidence that this column can actually survive the full fire. And finally, some summary. So as I mentioned a couple of times, that the analyzing just char depth in this kind of cases is not enough in natural fires. And of course, resistance to isofire and to natural fires, they are totally different things, especially with timber structures. And the failure may occur late in the cooling phase, and SAFIR seems to be able to capture this in numerical analysis. And also a couple of things to consider in the future work. So of course, the duration of the analysis, I mean, I could have continued the calculation even longer than 4 hours, just to be sure that there's no failure in really long at the cooling phase. And I didn't really consider the non-uniform temperature distribution, even though I had traveling fire. Well, it was quite fast traveling fire, so maybe not necessary here, but might have some effect in some cases. And I'm not sure what would be the worst case in traveling fire. What is the duration of preheating and cooling phases and so on? So there might be some different results with different duration for these stages. And also, it's really interesting if there would be some simple methods to assess the fire resistance in natural fires for timber structures, like DHB framework, for example. And it's interesting to also see what is the effect of material model. So now I have used the current Eurocode version material model, and it's probably going to change a little bit. So it's interesting to see what is the effect. And also connections are quite important factor here, as 3-hour resistance is required. So there are not too many tested connections for that. Okay, thank you, and hope we have some time for questions.
Thank you very much, Mikko. Very interesting presentation. It's great though to have a presentation on timber. It's indeed becoming more and more used, and so seeing those type of analysis is really nice. Do we have any questions? I don't think I saw any questions in the chat yet. Please feel free to ask questions in the chat if you have some. Okay. In the meantime, I do have a couple. So you mentioned, Mikko, that in Finland it is required to survive the full fire, right? So you have to capture this cooling phase and run the simulation for very long. Can you comment a bit further on that? When is it required to survive to full burnout? Is it as soon as you are adopting a performance-based fire design, or is it for certain classes of buildings?
Yes, it's in performance-based design, and it's if you have more than 2 stories, pretty much then it's always you need to have the full fire. And even for some 2-story buildings also, if they are like some high-risk buildings. But I would say that the problem in Finnish regulation is that they don't really say much more. There's only 1 page related to structural fire engineering and performance-based methods, so they don't give much guidance.
I see.
Other than that.
Thank you. And so you explained very well, and you showed with the isotherms at 75 degrees C the problem that we can have during cooling and the DHP approach. And in the end, in your application, the structure was able to survive. I noticed the columns had very massive section sizes, right? So I'm assuming that was the main factor. So here in your application, if I'm understanding correctly, the fire was not really a constraint or a designing case. I mean, you had columns that were big enough from the ambient temperature design, is that right?
Yeah, it seems that we asked the structural engineer to have at least 3 hour in isofire resistance for the columns, but it seems that they are actually having much more than that. They may have 4 hours or 5 hours actually. So that's really good starting point. for us.
Yes. Do you know where that came from? I mean, what loading case or what specificity of the building?
Yeah, I don't know, because there's really not seismic activity in Finland, so it must be like normal condition. But it seems quite massive. But I guess going to the upper floors, they will get more slender. So I guess there might be some challenges.
Okay, thank you. Okay, maybe one last question. Yes, I mean the properties, material properties, of course, are important in simulation. You mentioned you use the one that are currently in the Eurocode 5. Of course, that's what we have. There is a question on the thermal properties used when so you have the char layer, you have fibers when the temperature exceeds 300 degrees C, and then it will cool down. And can you comment on what happens with the properties, or what's the assumption with the properties?
Yeah, of course the properties don't retain, so they will, of course, the char cannot transform to solid wood anymore. So yeah, that's something I didn't mention. But yeah, like that's in SAFIR. I think it's inside the software that the timber properties don't come back like in the cooling phase.
Thank you. Very good. Thank you. Okay, we just have one more question, still a minute. What criteria did you use for window breakage? It's more on the fire modeling side.
Yeah, I actually don't remember right now, but I think we used like quite small temperature because we wanted to have the maximum fire there, and some I can comment on the chat about that, but I think the main objective was to have the maximum possible fire in that fire compartment. So we used really small temperature for that.
Oh, thank you very much, Anderson. Thanks a lot again, Mikko, for the great presentation. Again, very nice to see applications with timber and structural fire engineering applied to timber. Really appreciate also the answers to the question. Thank you.